So good morning, I am Krishna Kumar from Krishna's classroom. Well, we have been continuing our consideration of Rn, and in fact we looked at the basic structure of Rn and then as a vector space, and then we defined what are called linear transformations on Rn. We are interested to work on, in fact we will be interested to work on say more general maps than linear, but then the linear transformations or linear operators do play a very important role in the study of nonlinear transformations. Okay, but that we will consider later, but for the time being we would look at this class of transformations, and the linearity or the linear structure endows these objects with very nice properties, and now this is something that we want to explore. And now we have defined what a linear transformation is, and then we also observed that a linear transformation always maps 0 vector to 0. Now we also said that once you have a basis of Rn, then if we fix the images of the elements in the basis under the linear transformation, then it is completely fixed. And that is what we looked at. Said that every vector can be expressed as a linear combination of the basis vectors uniquely, and then with the linearity, if you fix the image of the basis elements under the linear transformation T, then T is completely defined for all x belonging to R. Now this is something which we did. Now that's a very interesting thing, that once you are talking about linear maps, all that we need know how it maps the elements of the basis. So the knowledge of the image of a basis fixes the linear transformation completely. Fine. Yes. Now we want to explore this further, and let us look at a special class of linear transformations, namely those which are one-to-one and one-to-one. So we take what are called let T belong to the set of linear transformations on Rn, which we denote by L, where Lrn is the set of all T from Rn to Rn, T linear. Is correct. So we are working on these objects. So we will put it this way. So this is the collection of all linear transformations on Rn. Now we want to talk about this space later, the collection of all linear transformations, but right now, for the moment, we will be interested only in some specific type of linear transformations. Now we look at the following. Let T be a bijection on, that means it is both one-to-one and one-to-one. Then you know that as a map, T is from Rn to Rn. As a map, T inverse is defined. How is T inverse defined? T inverse of y equal to x whenever Tx equal to y. This is well defined. I mean, this is, you see that T inverse is well defined. Because T is 1-to-1, T is onto, so T inverse is defined for every y belonging to Rn. And T inverse, this definition, that is, there is a unique image for every y under the map T inverse. This is the definition. Now the obvious question that you ask at this stage is it linear? Because to define T inverse, all that you need is the property that T is a bijection. So that map is well defined. But you know that T is a linear map. You are working on a linear space. Therefore, you have some expectation that some of the nice properties that T has also will be inherited by T inverse. So the question is T inverse linear? Okay. So let us investigate T inverse of y1 plus z1. This is equal to T inverse of y1 means there is some x1 and okay, we put here y2. Notation is nice. So this is T inverse of T x1 plus T x2. Okay. Now you see that this is equal to T inverse of T of x1 plus x2. That is because T is linear. And T inverse of T is the identity map. Therefore, this is equal to x1 plus x2. And that's equal to T inverse of y2. Therefore, T inverse is additive. Similarly, one gets to T inverse of Cy equal to C times T inverse of y. So that T is in T inverse is T, which implies therefore as expected T inverse is also a linear transformation from Rn to Rn. And you see that there are linear transformations which are not necessarily one-to-one and onto. Okay, so that is not an essential condition for T to be linear. For instance, if you just look at this one, so consider on, I take this as a remark, on Rn, which are not necessarily one-to-one and onto. For example, to take as an example, take T0, define for every, then T is or T belongs to, just verify this is very easy to verify, but T is not 1-to-1, nor T is also not on for this. Let's have a very simple example, and you can construct many more examples because you can talk about what are called projection operators and so on, which we shall use later, or at least in a course of linear algebra, you will be coming across such operators, which are not one-to-one. In fact, in R2, so this is an example. One here. So take one defined. So now you define T from 0. Okay. Now this is linear. But not. So this is a projection. This is a projection. That's an example of a projection. I mean, there are a lot of examples that you can construct. But this is not true. There are plenty of operators in Rn which are not one-to-one and onto. That means they are not invertible. So there exists several elements in LRN which are not invertible. So the invertible operators form a special class. Okay, so it's a subculture. Therefore, the invertible operators form a special class. It's an interesting class of operators which I want to example. Incidentally, there is one simple advantage that you have, because I want to make a remark. But see, some of invertible operators need not be invertible. Okay. So you give an example. I give it to you. So remark. Let me just write that. Now we shall talk about the product of such operators, and that I think we'll put it off the definition for a while and then make some noise about it later. Okay, so before that, we'll make an observation. If you are in a finite dimensional vector space like Rn, then you see that if a linear transformation is 1-to-1, then it is onto. Also, if it is onto, then it is 1-to-1. Therefore, we have a nice result here. Says you don't have to specifically talk about 1-to-1 and onto together. If you talk about, if you attribute one of the properties, then the other is automatically taken care of. But that has something to do with a finite dimensional, the fact that Rn is a finite dimensional vector space. And you need not expect the same result to be valid in an infinite dimensional vector space. So let us observe that in Rn, T is 1-to-1 implies T is onto and vice versa. In fact, we can write the following theorem. One can easily write a proof of this. It's not difficult at all. Okay. So we proceed as follows. See what happens. Okay. You know that make an observation. Range of T. The range of T. Is spanned by P of x1, P of xn, where x1 where x1, x2, xn is a basis for now this is very clear. Okay. Okay, this is very clear. It's a trivial observation. It can be given a format too, which I will give. Therefore, to show that T is onto, now you see that T is onto if and only if RT is equal to R. So it is enough to prove that RT is equal to. So what do you do? See, so to prove that RT is equal to Rn, see RT is, this is Rn, in general this is RT. P is a map from Rn to R. Now to show that Rt is equal to Rn, it is enough to show that you know Rt is spanned by Tx1, Tx2, etc. Txn. If I can show that they are linearly independent, if I can show that they are linearly independent, then Rt is a subspace. Oh, that's obvious. Rt is a this is easy to define, that you probably have already done. Therefore, Rt is equal to if and only if dimension of Rt is equal to A. That is if and only if therefore, what you have to prove is the following. Okay. So if you have T 1 to 1, then you want to show that this is linearly independent. So we assume, okay, the proof starts here. T is and this is equivalent to Px equal to 0, x equal to 0. Now that's quite easy. Because 0 is the only vector that gets mapped to 0. You would have seen in our example, two examples of operators which are not one to one. We have looked at one which maps every vector to 0. The other one was a projection where you see that a number of elements, that is whatever vectors that lie on the two axes in R2 under the map that we have defined, okay, just get mapped to 0. So it's not one to one. Okay, it is not one to one, obviously. Right. Therefore, it is enough to use this to conclude that T is one to one. And if you want, you give a very quick proof of this. That's all. Now let us see this. So we want to show that this is linearly independent. So plane independent, so that dimension of RT n, which implies RT equal to R. Okay. So okay, right. Then let us do the usual verification. So C1 Tx1 this is equal to T of C1 x1. Now what we want to prove, if you want to prove that Tx1, Tx2, etc., Txn is linearly independent, all that you need is that if this is equal to 0, then you want to prove that C1 equal to 0, C2 equal to 0, etc., Cn equal to 0. So, suppose this is true. Okay, then this is true. What does this mean? This means that see, we are assuming T is 1 to 1. Therefore, you have Tx equal to 0, x equal to 0. This implies C1 x1 equal to 0, which implies C1 equal to 0. So what does that mean? That means, see, C1 Tx1 plus C2 Tx2 plus Cn Txn equal to 0. This is because x1 x2 are linearly independent. Okay, this implies So it forms a basis for, so RT is a subspace spanned by n linearly independent vectors. Okay. Therefore, RT is equal to R. Okay. So T is onto. That is now let us prove T is 1. Okay. Assume T is very clean. See, it is enough to prove that T0 equal to 0. Okay. Okay. So what you have? T is onto, which implies, so since T is onto implies RT is equal to Rn, which implies which spans RT is a basis for R. Okay. Now you take X belonging to R. Let X be equal to C1 X1. Now we want to prove that Tx equal to 0 implies X equal to 0. So what about Tx? Tx which belongs to, this is equal to, well, I am skipping one step at this stage, and this you can easily show that. Therefore, Tx equal to 0. Equal to 0. Now this is a basis. Therefore, this implies C1 equal to 0, Cn equal to 0, since what does this mean? Which implies x equal to 4, which implies, so that completes. So it is see, in a finite dimensional space like Rn, in fact this is more generally true in a daily vector space also. You see that T is 1 to 1 implies T is 1. Now, we mark for instance, you take this one, so consider where EI this is not finite sequence, but it's an infinite sequence. That means the ith place it is equal to 1 and elsewhere it is 0. This is a standard basis for what you call a sequence of real numbers. Okay, right? A sequence of real numbers with the property that it is 0 from. So we call this the following: C naught naught, where C naught naught is the set of all sequences of real numbers which is 0 from some stage onwards. Real numbers Xn such that for every n greater than some particular n, depends on x is equal to x. That means it's a sequence which vanishes from some stage onwards. So that by making finite sums of this, you can construct this. So you can easily verify that. Slowly stepping outside the finite dimensional spaces. basis for C naught naught. Okay, that's fine. Now on C naught naught, let us define an operator. So define P of the sequence x1, x2, etc. to be equal to etc. Then show that T is 1 to 1. But T is not on. Verify. Okay. T is not on to because the range consists of all those elements in C naught naught whose first entry is 0. So it's only a part of it. Okay. Now you can verify that this is 1 to 1. That is quite easy to do it. You choose an x, choose a y, and compute tx, compute ty, and show that if tx equal to ty, then x equal to y. I leave that completely to you and you explore that. So that's up to you to explore and convince yourself. Therefore, you see that the statement or the theorem that I have proved here is not valid when you work in infinite dimensional spaces. Whereas in the finite dimensional space, you have the luxury that if you say T is 1 to 1, then it is on to, or if you just prove T is on to, then it's already assured that it is 1 to. There's a finite room there, that's all. That's the reason. Okay. Whereas here you have an infinite room. When you push the whole thing by one step, still you can accommodate it inside your space. That's possibly the reason. That's an interesting aspect of it. Okay. So now let us look at some examples where the operators are not invertible. Maybe I can do that and it's not difficult. Now you see that I don't know, I think I already said that if you take in R1, if you take in R1. Okay, now you see one thing that you observe is that even if T is 1 to 1 on to and T0 equal to 0, or Tx equal to 0 implies x equal to 0, you cannot conclude that T is linear. So T equal to linear has to be specifically set. Okay. See, T 1 to 1 on to T linear or T0 Tx equal to 0 implies x equal to 0 need not imply T is linear. So an example is you take R1, on R1 consider Tx equal to x cube. This is not linear, obviously, but you can show that this is 1 to 1, this is on to, and this is equal to 0, Tx equal to 0 only when x equal to 0. Now, I think maybe, see, these are all important things. You see what it is actually. If you draw the graph of this, so you are making a map from here to here. So if you draw the graph of this, see, it's something like this. This is okay. So what you are doing is you are taking an x here and mapping it. This is your Tx. Now clearly you see from the graph it is obvious. See, Tx equal to 0. Only if x equal to 0. Otherwise it is not equal to 0. And T is both 1 to 1 and on to. So it's a map from this copy of R to this copy of R. And it's also an on to map. It's also a 1 to 1 map. All these are clear from the graph. So I think it's always go to lower dimensional spaces where you can actually draw pictures and get a feel for things to understand the concepts. Okay. And you also see that if so this is 1, 2, okay. So T 1 to 1 on to need not imply T something. So you look at this one. T from Rn to Rn defined by A, where A belongs to Rn and not equal to 0. So you see that this is not linear. This is 1 to 1. T is 1 to 1 on to, but T x equal to 0 does not, or even T0 is not equal to 0. Okay? And therefore T cannot be linear, because if T is linear, then you have already shown that T0 is equal to 0. So this is not linear. So one cannot omit that statement that T is linear whenever you talk about 1 to 1, 1 to 1. Okay? So I think the graph corresponds. So okay, right. So these are some of the little things that I think is better to know. Now let me also talk about the change of basis, or the change of coordinate system. Quite often, when you work in mathematics or in a space like Rn, a change of coordinate system will be much more useful to understand what is going on. Okay? Right? We'll talk about it when we talk about diagonalization. I mean, it will be very clear. Why do you go for change of basis? Now, I think I will make some remarks about that also, although I may not go very deeply into diagonalization and so on. But at least I will talk about the premises under which you seek diagonalization of an operator. Whatever that be, I have not defined it yet. Okay? But let us be clear about something. For that, we look at some nice examples. Okay. So you see that a change of, suppose you have two bases. Say, let and let y1 basis. Now there are two bases that we look at. Now define a linear map such that Pxi Pxi equal to 1. Okay. Then you know that T is 1 to 1 onto and isomorphism. What does it mean? It means T is 1 to 1 onto a structure preserving. Here, the structure that you have is linear. Now you talk about isomorphism in various contexts. For instance, one group into another. So then you will be talking about the group structure from a ring to another ring. Then you will be talking about the ring structure, or from a field to another field. You will be talking about the field structure, or from one module into another. So, you know, all this is essentially the maps which are 1 to 1 and on to and preserves the structure. So here you see that if you take a linear map from Rn to Rn, okay, which is defined in the following way, that you take one basis, you take another basis and this one, so with that you can define a T. Then here T is an isomorphism. T is an isomorphism. So by connecting a basis with another basis, you can get an isomorphism. Conversely, suppose you have an isomorphism. Okay. Suppose T from Rn to Rn is have, it is 1 to 1, 1 to, and structure. Preserve. What I want to say is this. Let Xn be a basis for then Px1 is a basis for, I leave it you to prove this. So every basis is mapped to a basis whenever T is an isomorphism. Conversely, if you have a basis mapped to another basis as defined here, Txi equal to Yi, then T is an isomorphism. Therefore, the two concepts are synonyms. Synonyms means one and the same. So every basis gets mapped to another basis here. There, every if you have defined like this, then it becomes T becomes an isomorphism. Therefore, given two bases and the connection Txi equal to Yi, then you are inducing an isomorphism. Okay, or Yi has been generated by the isomorphism as Tx1, Tx2, etc. Txn. Okay, so that's the idea. Okay. So the two ideas are the same. If you have an isomorphism, then it maps every basis to a basis. Okay. If you have a map which maps one basis into another basis, as defined here, it's a linear map, then that is an isomorphism. So these two concepts are the same. Now let us look at something, one little example to highlight some of these ideas. For example, let us take R2. Let us take R2. Now let us take a basis B1, the standard basis. Okay. Now what I do is I map from R2 to R2 the following map. So let me define, let phi V1, which is equal to phi of 1, 0, I define it as minus 1, 0. Or let me take minus 1. Just, when the other one is right. Alright. So I take phi of V2, I write as one. Now this is your x1 b1 is this, therefore b2 is now the basis 0 minus 1 1. This is the image. So TB1 is actually phi B1 is B2. Okay. So B2 is essentially this one, that is B2 is essentially so the first question that you ask is this a basis? Is B2 a basis? Before that I want to say the following. Phi is extended on R2 linearly. So once it is defined on this, you can easily extend it on the row space as linear combination, and the moment you put linearly, then it is well defined. Okay, then phi is an isomorphism. Oh, okay. Is B2 a basis? Now this is the question that you ask. That's quite easy to verify that independent, and therefore it forms a basis for R. Okay, therefore B2 is a basis. Now let me call this a coordinate system. Why I call this a coordinate system? Now let me take a copy of R2. A copy of R2 is created out of R cross R with the two vectors 1, 0, this is E1, and the 0, 1, this is equal to E2. Okay. Okay. Now we get another copy of R by keeping. So this is our basic space is this one. So this is the basic vector space that we have. So you have got some TE1 is what? This is the vector 0, -1. This is equal to phi E1. And then I have the vector 1, 1. Therefore, what I am doing is I am making a new coordinate system. I am making a new coordinate system with these two as the reference axis. Okay. So you see that they are not along the same direction. So this is obviously it forms a basis. It forms a coordinate system. Okay. Now you choose any vector A1, A2. I just choosing an arbitrary point. What does it mean? It means that this is equal to A1 E1 plus A2 E2. Okay. Now let us apply phi to this. If I apply phi to this, now this point goes to, okay, this point goes to what? So I have, so phi of A1, A2, if I compute, this is equal to A1 into phi E1 plus A2 into phi E2. and this is equal to and that is essentially A2 minus A1 plus this. So it goes to some other point. Okay. Right? Now, what will be the coordinates of the same point with respect to the new basis? That's what we are trying to explore. Okay. So, if you explore this, the same point is, because we have the original reference system here. So, you have the A1, A2 here, A1, A2 is somewhere here. Now, you see, what will be the new coordinates that you obtain? The new coordinates that you obtain is going to be what? So, this is your A1, A2. Will be, see, according to the new coordinate system that you have, see, this vector is to be obtained as a scalar multiple of this plus a scalar multiple of this. So what one obtains is you complete the parallelogram into this point, and this lengths you have to complete. Okay. So you see that in the original coordinate system, it will be what? See, the coordinates of this is going to be A2 minus A1 plus A2. So with respect to this coordinate system, it is going to be the point A2 minus A1 plus A2. Okay. Okay, so this is how you get an arbitrary point. A1, A2, its coordinates are going to be different. So what let us explore that. Within the framework of E2, you see that A1, A2 gets mapped to this will be identified by this point. Okay, so this is in R2. So phi of it's all within the framework of this. Okay, this is where it really goes to. Okay, this is the map. Now you can even represent this as a matrix. So let me compute the matrix that does the trick. So it's 0, 1, and this is equal to -1. Okay. So you see that phi is now represented by a matrix. I am just recalling your knowledge of matrix theory, so that it gives a matrix multiplication can be represented by a matrix. So phi is now represented by a matrix and the operation is represented by so we have discussed everything in the framework of E1. Okay. This is a way of representing the linear transformation. And you can actually see that the determinant of this is an invertible linear transformation, because you see that the determinant of phi is equal to -1. Okay. Phi is invertible and determinant of okay. So let me write here. So this represents the matrix. The phi is the matrix phi is a matrix representation of phi with respect to the basis E1. So everything discussed in the framework of E1 and E2, this is the matrix representation. Now we will look at whatever experience we have on this particular example. We will try to rework it. Okay, the same point is identified by this. Now this can be reworked by in the following way. So let us work it out. Just draw a new picture. Okay. So you have A1, A2. So this can be looked upon as, so you have R2. This is in the framework of, so this is actually A2 into So this is actually in the framework of E1, E2. Now this is actually in the framework of, say what you have E2, E2. Yeah. To this point. So what is happening? So you are taking an A1, A2. Okay, let us take a specific point. For instance, you take say 1, 1. Where does this go to? This goes to the point A2. So this point goes to A2 is 1. This is equal to 0. So 1, 1 actually gets mapped to 1, 0. This is how it goes. It's not projection. It's not a projection. This map is an invertible map, but it goes to 2. So for instance, if you were to take the point 1, say 1, 0, what is the image of this? 1, 0 will be mapped to 0, 0, minus 1. So go to this is the mapping side. This is the mapping side. Okay. Right. And what is the image of this? This point will be mapped to what A1 is minus 1, A1 plus A2 is minus A1 is 0, A2 is equal to minus 1, therefore this is minus 1. So this will go to the point minus 1. Okay, now compute this. So what is phi of? This is equal to minus 1, 0. So this is equal to minus 1. You see, it's all a funny way in which if you start with a point and look at the part of this map under phi, and you get all these maps coming. Okay. So this is the general map, but it's a linear map. Interesting, it's a linear map. Okay. So we start with 1, 1. Look at the image of that. And then look at the image of that. Look at the image of that. Look at the image of that. You just check whether my calculations are right. Okay. And you also see the same point under the new coordinate system takes a different designation. Okay. So if you take the new designation, then the same point has a new designation. So what is the image of? So you ask the following question. What is the image of? A2, you write this as B1 into so this is actually back to B1, B2. With respect to the new coordinate system, this is with respect to B1, B1, B2. This point is the same point. So let us connect this. So you want to look at the same thing. So this is equal to B1, B2, B2, and that has to be equal to A1, A2, which would mean that A1, B2 equal to A1. If B2 is A1, then you have the second equation minus B2 plus B1 equal to A2. Therefore, B2 is A1. So I have B1 equal to A2. So this is equal to B1 equal to so the representation of A1, A2 with respect to is okay. So this is the representation. So the representation actually changes. Okay, right? This is the important aspect. So when you change the coordinate system, the representation that you have changes. Okay. So you use a different coordinate system, you get a different representation. So every time you map the point in R2, so you can even conceive of that as a map from A1, A2 to A2 plus A1 to A1. So this is another way of conceiving the same transformation. For example, let me take the point A1 equal to 1, A2 equal to 1. Let's take this. If I take this, what happens is, see the point 1, 1 will get moved to 2, what? This is the new representation in terms of the new. So you have one copy of R2 and on that another copy of R2 is superimposed. Okay, and this is what happens. So these are the various pictures that you have in connection with this. So this is not fine. This is not fine. This is a representation, new representation that you are talking about. So I think I will stop here. Okay. So you introduce a suitable basis to get a new representation. Maybe I can bring little more clarity into the working of these things next time. Okay. Thank you very much.